So welcome. I think this is the third talk in the CLARIPHY series. And to me, this talk, this series of two talks is really exciting because I have two students that work in collaboration with totally different labs. So first will be Braden, who will be talking about some work that he's doing in collaboration with the CMS experiment at CERN. And then Eleni will be talking about work that she's doing in collaboration with the Theory Center at Jefferson Lab. And so typically the subfields, my students that work in the various subfields are kind of divided up and they typically never present together. And so to have two students working on related conceptual problems at the intersection of AI and their subfield application area is very cool to me. And so, so I had titled this There and Back Again, interfacing between theoretical parameters and experimental observables, because both of the students are working at that interface. So, so mapping to and from in the respective cases, theoretical parameters and experimental observables. And so their work is analogous to each other, even though they're working in collaboration with totally different labs, different people, different application areas. So this is a really neat environment. This CLARIPHY group is a really neat environment for us to be able to present that work together. So I think without any further ado, I will introduce our first speaker. And yeah, I'm such a super fan of all my students, and these two are no exception. So first up, we have Braden Kronheim, who is already killing it in 2021 with the first author publication that just came out, and he'll be talking about that work today. So I asked each speaker to speak for 20 minutes, and we have about 10 minutes each for questions, and then we'll be done. So whenever you're ready, Braden, take it away.
Okay, can you all hear me? Okay, sweet. Okay, so my project is on using Bayesian neural networks to make fast predictions from high-dimensional theories, working with Dr. Kuchera, Dr. Prosper, at Dr. Kuchera Davidson and Dr. Prosper at Florida State. So, okay, the general motivation for this project was to find a way of making rapid predictions from expressives beyond the standard model theories with large numbers of parameters. Using some form of machine learning is a typical approach to this problem, and there are many different techniques to choose from. As machine learning inherently provides an approximation of the true value, we wanted to find a method which would provide a meaningful estimate of the uncertainty in the predictions, as ML methods can often yield confident but highly inaccurate results when asked to make predictions from outside the region they were trained on. For example, we want something like this, where instead of a single prediction, we get a distribution of predictions, which then can be compared to the true values in a test set to judge the reliability of these output distributions. Okay, so again, deep neural networks have been shown to be very effective at solving regression problems, but the typical approach of using backpropagation to solve these do not provide reliable uncertainty estimates because they typically just provide a point prediction, which will be equally definitive whether it is accurate or inaccurate. By assigning a prior distribution to all the network parameters in a deep neural network, we can obtain a posterior distribution of all the possible reasonable networks using Bayes' theorem given the training data. So the result of this is that instead of a single prediction from a single network, we will get a distribution of predictions from a distribution of networks. And we can use the distribution of these predictions to kind of assign an uncertainty to the prediction. So, okay, the Bayesian approach is we let theta denote all of the parameters in the deep neural network, and we let D be the training data. Then using that, a straight up application of Bayes' formula gives that the probability of the network parameters given the data is this expression here. So if we let f be the neural network that we're using, and we let y be a prediction, and x some point in the parameter space of the BSM model, we can compute a distribution over all of the y using this formula here, where this probability of theta given d is the one from Bayes' formula. The difficulty with this equation here, though, is that we need to integrate over every single possible network parameter, which is not possible given the thousands, hundreds of thousands, or millions of parameters and their continuous possible values. So given that, Markov chain Monte Carlo methods present a well-understood way to approximate these really high dimensional integrals. And it's been used in areas such as lattice gauge field theory to great success. So the specific Markov chain Monte Carlo method we're going to be using is Hamiltonian Monte Carlo, HMC, as it's one of the methods of choice for dealing with these sorts of problems. In this sampling area, we are going to have a neural network be represented as a list of all of its parameters in a really high dimensional space. Then we're going to treat the negative log likelihood of the data as a fictitious potential energy well. The log likelihood it's just a log of the probability of the data given the network parameters times the likelihood of the parameters, where this term here kind of corresponds to how good the predictions of a network is, and this term here corresponds to the likelihood of the network parameters given their priors. And we use the log value of it because it is more, it is easier to deal with numerically. So, and then once we have the list of parameters and we have this potential energy well, we then assign a random momentum in each of these dimensions, and we use Hamilton's equations to figure out how this particle, the neural network, moves throughout the parameter space. So we would start here with some neural network, assign the momentum, use Hamilton's equations to move to the next spot using a differential equation solver, and we move a certain number of steps, take the next network, and we just keep repeating this process with different random momentum, and eventually this will work itself into the distribution that we are interested in. Okay, so in order to do this, we used a package called TensorBNN, which we wrote to do this. It is based on TensorFlow, which provides an extremely powerful back end for running machine learning tasks, because it compiles training and inference tasks into very efficient computational graphs that can utilize GPUs and multi-core CPUs to dramatically speed up the calculations. TensorFlow itself, however, doesn't have a direct means of doing Bayesian neural networks, but there is a related package called TensorFlow Probability, which has Hamiltonian Monte Carlo samplers built into it, which we use to make a more general purpose framework for training BNNs called TensorBNN. And the goal of it was to make it easy to create networks and provide several analysis tools for examining how these trained networks performed. So if you want more details on the actual package, you can go see our paper on arXiv, which describes how it works, and our GitHub page, which actually has the code and some examples. So applying it to our actual theoretical model, we were looking at the phenomenological minimal supersymmetric standard model, and this beyond the standard model theory provides a excellent playground for looking at how Bayesian neural networks can be used for theoretical modeling, as it has a fairly large number of theoretical parameters, but not an unusably large number of them, and it is of some theoretical interest. So the kind of the summary of the it is we have 19 free parameters, which are all listed over here along with their descriptions and the ranges we're using for them. The main observable we were interested in was the next to leading order total supersymmetric cross-section. One of the reasons this one is interesting is because it is such a slow observable to predict using the typical SUSY codes, as it can take up to 3.5 minutes each for each set of parameters. And then we used these codes to generate the training data that we used for the paper. We also looked at the predicted Higgs mass, as well as the theoretical viability of these PMSSM parameter point combinations as determined by the SUSY codes. Okay, so cross-section again was the observable we were most interested in. And to study this, we generated about 200,000 PMSSM points, and we used 160,000 of them to train. We used a network architecture with the 19 inputs, 5 hidden layers of 50 perceptrons each, and a single output. After a period of burn-in, we performed 13,500 sampling steps, and we kept 1 out of every 100 of those. And over here, we have a graph of the posterior distribution. So it's a distribution showing the probability of a given prediction given the input X and the training data, which is represented from the training of the Bayesian neural network. And you can see how we get this nice distribution, which is mostly Gaussian, and it's right over the correct value. So overall, the predictions using the Bayesian neural network had a percent error of 3.34%, which is quite good. And if we use the distributions like this one to construct 3 standard deviation credible intervals, which we can treat as confidence intervals, the coverage is 99%. So essentially what this means is, while from a Bayesian statistics point of view, the credible interval is essentially just the spread of this, we can use some frequentist statistics and just treat this as an uncertainty estimate on the predicted value and fit a Gaussian to it, as it is indeed mostly Gaussian, and then use the standard deviations of that as a confidence interval. And the coverage means that if we look out to 3 standard deviations on all of these fit Gaussians, that the correct value is within their range 99% of the time. Additionally, when we ran these predictions on GPUs in large batches, we were able to make the predictions 15 million times faster than the original supersymmetry codes. So that's a big one. Now, okay, so here we have 2 plots of the cumulative distribution for the difference in percent error between the BNN and the leading order predictions as compared to next to leading order. A negative number here implies that the leading order was better, and a positive indicates that the BNN was better. So from this graph, we can see that the leading order was better about 1% of the time, but the BNN then was better 99% of the time. And then these next 2 plots present a look at how the spread in the Bayesian neural network predictions correspond to the spread in the network errors. Now, for this graph here, there are actually 3 components to it: the actual errors in the predictions, the distribution of errors in the predictions, and the distribution of predictions from the Bayesian neural network. So each small blue dot represents the error of the mean of the Bayesian posterior for a single example. The solid black line is the mean of these errors in a given bin, and the dotted and dashed lines are plus or minus 1 and 2 standard deviations of that distribution. So the distribution of the blue dots. Thus, they are the spreading the error of the actual predictions. To form the yellow and the green bands, looked at the variances of the Bayesian posterior averaged them across each bin, and then took the square root to assign a standard deviation. The green band is the mean error, plus or minus 1 posterior standard deviation, and the yellow band is plus or minus 2 standard deviations. So this indicates that the Bayesian neural network had a larger uncertainty than the errors in the actual predictions, though it wasn't by that much. Additionally, looking at this bottom histogram, which has the counts of the training examples used, we see that the width of the Bayesian, the uncertainty of the Bayesian predictions was larger when we had less training data, and it was smaller when we had more training data, which is exactly what we would expect. Okay, so the second observable we were looking at was the Higgs boson mass. For this, we used a training data set of 450,000 points. And the network architecture was again 19 inputs, 5 hidden layers of 50 perceptrons each, and a single output. Here we performed 2,850 HMC sampling steps, used 1 out of every 10 networks. And then we kind of divided the predictions into 2 categories based on whether or not 3 standard deviation credible intervals overlapped the range of 123 to 127 gigaelectron volts. So the motivation for this division was to determine whether a given set of PMSSM parameters predicted a Higgs boson which was reasonably close to the measured value. Hence the 123 to 127, right around 125. So in the overlapping region, we got a percent error of 0.1%, and we got a coverage of 87.4%. In the non-overlapping region, it was 0.14 and 86.7%. So these percent errors are much lower than the numbers we had for the cross-section, but the coverage is worse. So given that these regression results weren't quite as good as we had hoped, we also treated this as a classification problem to simply classify whether a prediction would a set of PMSSM parameters would give a prediction in this region. And when we did that, we got a precision of 0.926 and a recall of 0.997 and an F1 of 0.96. So essentially this means that using this as a classification algorithm, we'll be able to find basically all of the PMSSM parameters that give reasonable Higgs masses at the cost of having a number that wouldn't actually include it. Okay, and then the final thing that we were looking at was the theoretical viability. Here we used a training data set of 400,000 points, same network architecture, and we did 1,750 HMC sampling steps. So the posterior distributions here looked a little bit different, as it was a classification and not a regression task. If we look over the full range of what the classification values could be from 0 to 1, we have a lot of graphs that look like this, where the actual predicted distribution is super tightly clustered around 0 or 1, and it's not really visible on the full range. But if we zoom in, we can see that it actually does, there is some width to it, some degree of uncertainty, but not very much. And it's also not quite as Gaussian as the other, as the Higgs mass and the cross sections were. So as this is a classification task, we use 2 different strategies, one to give the best overall performance and one to minimize false negatives. The reason behind minimizing false negatives is that false positives can be found just by running the actual supersymmetry codes, because they will give an error and they will not work. But a false negative would be a set of parameters thrown out even though they are actually valid. So by minimizing false negatives, you minimize the number of potentially interesting points that are thrown out, even though they shouldn't be. So we obtained the best overall performance just by taking the average output of the neural network and using that as the classifying value. And doing that, we got a recall of 0.955, a precision of 0.953, and an F1 of 0.954, so all very similar numbers. And to minimize false negatives, we took the mean prediction and then we added on 3 standard deviations of this distribution down here. So the reason behind this was that it would include all of the predictions that the Bayesian neural networks were not sure on as positives. That way we could then look at them later to see what was going on. And when we did that, our recall went up to 0.982, but the precision in the F1 dropped a little bit. All right, so for further study, given the success of TensorBNN in replicating these PMSSM cross-section predictions, as well as our other targets, it would be interesting to test the effectiveness of it on other potentially more interesting theoretical models. We can also extend the package to include other layers, such as convolutional layers. And an autocorrelation study that we performed showed that the networks were still fairly highly correlated, suggesting that we need a greater lag between the sampled networks, and therefore longer Markov chain Monte Carlo chains, which would then motivate the need to reduce computation time, as it is still fairly computationally expensive. Also, decreasing this autocorrelation would likely improve the correlation between the Bayesian uncertainty intervals and the actual errors in the predictions. So the package already has an algorithm to adapt the step size and the leapfrog step variables, which are used in the differential equation solver, but we could tune this further, which may be beneficial. Additionally, we could use the no U-turn sampler, which is a variant of the Hamiltonian Monte Carlo sampler, to reduce the correlation length of the sampling. We've experimented with this a little bit and it seems promising. Additionally, we could look to use the Riemann manifold Hamiltonian Monte Carlo sampler or the learning to HMC sampler or other ones. So that was my talk. Any questions?
All right, thank you so much, Braden. If we could all give him a virtual round of applause, that would be fantastic. And Braden, just imagine a room full of people applauding you. I think that, so first of all, I wanted to mention, so we pointed out the archive paper in the TensorBNN package, but the physics results are also recently published in Physics Letters B, so you can find those results as well. So I think we'll take questions now, and if you use the hand raising feature, I can call on people. We have a few minutes available for questions.
Can I ask a question direct? Oh.
Hello, yeah, Pablo, go ahead.
So thank you for the talk. I will take a look at the paper to have more details about it. I just wanted to know how confident you are that the parameters or the samples that you have explored so far are representative of the whole process that the actual cross-section code does. Like, I'm trying to think of what if at some point you want to make a prediction on something that is too far away from the data points that you have had, and how will you be sure that whatever your Bayesian neural network prediction tells you will still be valid on that region?
Yeah, okay, so that's actually in one of the main benefits of the Bayesian neural network approach, is that it should be able to handle that, because all of the networks it has sampled are largely independent of each other. If they are asked to make a prediction in a region which is very different than what they were trained on, they should all have very different responses to it, and therefore produce a very wide range of results, resulting in a very wide range in predictions, which we can then see that happened and then either throw out that result from the immediate analysis or just use one of the actual supersymmetry codes to look at that point to see what actually is happening there. I haven't directly tested this on, like, I haven't asked it to make predictions from like wildly different regions, but the fact that the coverage was so good on the test set, which is stuff it wasn't trained on, that indicates that it should behave as we were expecting in the regions far away from what it was trained on. We've also, using like smaller examples, we have seen that behavior happen where you move away from the data that it was trained on, and then the uncertainty in the predictions just gets very, very large.
Yeah, so you did look into that for non-SUSY examples. Yeah. And it made sense in that realm. Okay, yeah, and we have a question by Dr. Vossen.
Yeah, thank you. You can call me Anselm. Yeah, very nice talk. So I actually have for maybe a naive question. It just has to do with my ignorance. So if I understand correctly, so basically you showed how you generate these basically the distribution in the posterior probability. So, but your equation had this prior on the weights. How do you come up with those? Like,
okay, yeah, that's actually a really good question because hold on. Sorry. Yeah, because there's not really a super obvious choice for choosing what the prior should be, because we don't really have any prior knowledge of what the weights and what the biases should be in the neural network to produce the values that we want. So what we do is we just assign fairly broad Cauchy distributions to them. The motivation behind this is that it allows them room to kind of move around and settle on values that work well for the predictions, but we don't lock them into like specific values, but we do give them centers around 0, which is what we expect from a neural network. But beyond centering them there, there's not a super clear choice for what they should be. One of the features we built into the TensorBNN code was that you can actually, after you've trained all of your networks and you have finalized models, you can actually go in and change what the priors are for the layers, and then recalculate what the and then essentially reweight the networks that you've already sampled to what they would have been given the new priors. And while if you change them dramatically, it's quite possible that the networks you have sampled already would become very unlikely, and the reweighting wouldn't provide useful results. But if you do small tweaks to them, then you can actually still get meaningful results from the networks you have sampled, but with a different prior.
I mean, thank you. So, but I mean, one difficulty is obviously that these weights don't have any physical meaning. So you can't really assign a prior based on the theory or anything like that.
Well, there's no clear way, at least that I'm aware of interpreting the values from the deep neural networks to have like physical meanings. If you use a different model than a neural network, you could assign much better priors to the values, but the actual neural network architecture that we're using doesn't have any clear connection to like a theoretical model.
Yeah.
It's
No,
just, yeah.
I understand. Yeah, thank you. So that makes sense.
Yeah, so unfortunately we're out of time for this, but let's give Braden one last round of applause while Eleni brings up her presentation. So Eleni's work is actually working on the inverse of what Braden just described, but for a totally different application. And Eleni is tuning in to present to us from Greece. So Eleni, whenever you're ready, you can take it away.
Okay. Hi everyone, my name is Eleni, and today I'm presenting my machine learning techniques to map from experimental cross-sections to quantum chromodynamic theory parameters. And this research is done in collaboration with Jefferson Lab, as well as Old Dominion University. So what is quantum chromodynamics? Quantum chromodynamics is the theory that pertains to quark-gluon interactions and the strong force, and particularly as it contains two components of hadrons. And so specifically, we're concerned with experiments such as those done at Jefferson Lab, where an electron beam is accelerated and collides with proton targets. In addition, we also have other experiments in facilities where the electron beam collides with proton and neutron targets, also known as deuterium. In addition, because quarks and gluons cannot be measured directly, this process results in deep inelastic scattering. And as a result, we get an image of the structure of the hadrons. So more specifically, the important information that we care about, theoretically, is stored in what we call a parton distribution function, which describes how quarks and gluons are distributed. The parton distribution function is made up of the momentum fraction of a parton, in which the number of partons of type I in an interval x and x plus dx are measured in the function that we see here below. An example of such parton distribution functions is shown here on the tables here. And as we see, we have different partons that we care about, such as up and down quarks, as well as relationships between them that are theoretically important. So that brings us to our initial problem, which is, well, initially in Jefferson Lab, in the theory center of the Jefferson Lab, we have a mapping going from parameter space to observable space. So parameter space relates to the parameterization of the parton distribution functions that is trying to parameterize the observable space, which is the experimental cross-sections observed at the experiments at the lab. And that is done with the theoretical models that Jefferson Lab theorists have come up with. Our problem is actually the inverse problem of going from observable space, and so the experimental cross-sections, back to parameter space using machine learning. This problem is inverse because parameter space in this case actually refers to multiple sets of parameters that can fit one single cross-section in observable space. And as a result, because either of the physical real multiple solutions that a cross-section can correspond to, either because of uncertainties in our experimental data, we need to make a mapping that is not one-to-one. So before we go into that, let's talk a little bit about the data that the theorists come up with using the theoretical models at Jefferson Lab. And so this is done in the Jefferson Lab Angular Momentum collaboration, where the theory model parameters are fit using regression to parameterize the experimental data that the experimentalists give them. This fitting is particularly done in the tuning of a chi-squared regression fit. And as we can see here, we have the different theory model parameters described, as well as some normalization parameters. And we also have the experimental data along with their statistical and systematical uncertainties. And this is the chi-squared fit that we care to minimize. In addition, however, we now move on to our inverse problem. So the inverse problem of going from observable space to parameter space using machine learning is not an easy feat. In fact, we first have to consider whether machine learning is an accurate method for this. In the graph below, we see a simple neural network using simple backpropagation, trying to fit a problem of a function having multiple y values for the same x value. We see that simple machine learning is not a great tool for this, as in fact, it cannot produce multiple y values as seen on the red line. And as a result, if we're trying to consider this problem using machine learning, we need to provide a technique that can provide multiple solutions. To achieve this, we use what is called a mixture density network. And in a mixture density network, we have an architecture that instead of producing an input-output pair, produces an output of 3 values. These 3 values correspond to a pi, a mu, and a sigma squared, which are then used to generate a mixture of Gaussians as seen on the graph right here. The mixture of Gaussians can then be sampled to actually get different multiple solutions. So for example, in this specific graph, we can sample this mixture of Gaussians and get, for example, the 3 most common solutions that we see here, as well as with the probability of them being the accurate ones that the theorists are also going to predict. So our architecture can be shown here on the left, where we get the cross sections coming both from proton and deuterium data. And then we get our output of pi, mu, and sigma squared that we then generate our mixture of Gaussians with. However, we have also used different architectures to solve this problem. So first, we have used a supervised autoencoder architecture shown on the left. In this architecture, we start with the actual experimental cross sections, and we do a dimensionality reduction and end up with a number of nodes equal to the number of parameters we want to parameterize these cross sections to. Then we regenerate all the way back to our initial cross section dimensions. This is a supervised autoencoder, and it's specifically supervised on both the latent space, so both the parameters as well as the cross sections that come out. And as a result, this is supervised on the pair of parameters and cross sections. However, we realize that the autoencoder architecture does not provide multiple solutions, as we have described in the beginning. And as a result, we realize that to solve this problem, we actually have to embed a mixture density network layer in our autoencoder architecture. As a result, we have come up with this graph on the right, which is our architecture for what we have called the AE-MDN. So here, the latent space is no longer the parameters, but it is an MDN layer that creates the mixture of Gaussians from which we can sample our multiple sets of parameters corresponding to the cross-section that comes in. The data that we use for this comes in 2 forms. So first, as a test that this works, we have tried a simplified model where our cross-sections of proton and neutrons mimic some simple structure functions, and we have only used 10 free parameters. In addition, we supervised on the parton distribution functions. So our test of this working was only done on up and down parton distribution functions. More importantly, we moved on to deep inelastic scattering data, which was actual experimental data coming from different experiments, such as SLAC, BCDMS, NMC, and HERA. And as we see, these dimensions greatly explode to a big number of cross-section points, as well as 25 free parameters. The parton distribution functions we're concerned with are also greater, and we see that we now have gluon and strange quarks in addition, with relationships between them. So as far as our results go, we can first look at the simplified model, and we have plotted 3 different spaces that we care about, so parameter space, PDF space, and observable space. Here, the green lines represent our MDN models, the red lines represent our AE models, and the blue line is the JAM theoretical prediction. As a result, the most important space that we should look at is the parton distribution space, and we see that we're very, very closely with both models predicting around the theoretical prediction, which makes us confident that this test is working, and we can now move on to the deep inelastic scattering data. For the deep inelastic scattering data, we have decided to only plot the multiple solutions coming from the mixture density network. This is important because the mixture density network provides this extra functionality. And as a result, we wanted to test whether our multiple solutions can actually correspond to some of the multiple solutions that different fitting methods in JAM have come up with. As a result, we have sampled our mixture of Gaussians multiple times here. And we can see that the trends, even though they're not exactly the same as those that we see in the JAM architectures, closely relate to them. And so we can see, for example, that some of these patterns correlate. So we are confident that our mixture density network sampling can provide a lot of the same sets of parameters or a lot of the same distributions that we would get from JAM. And we're confident that we should continue trying this method as a viable method. And we also want to obviously make our bands narrower and more closely relate to JAM. So we want to do better on this plot. In addition, we present an average and error plot. So in the average plot, we only look at our most probable solution. So the one that is most probable to come up. And we see that unfortunately, the mixture density network is a bit less narrow than the autoencoder. So as a result, the mixture density network, because of its ability to predict multiple solutions, cannot come up with as narrow a solution. So it's not as accurate as we would expect the autoencoder to be. On the right, we see a graph of the kinematics. So specifically in the areas that we're predicting well, in kinematic of the DIS global data sets. And these two are error plots of the AAE, right below the kinematics, and then of the MDN networks. And as we see again, the AAE has a closer relationship to getting an accurate chi-squared result than the MDN. So again, it is more accurate. However, it does not provide the functionality of multiple solutions that we're also concerned with. So at this point in the research, we decided to take a step back, because while the result was promising, it was important for us to understand how applicable the model would be to universal fits. So basically fits from different collaborations or different fits from the same collaboration. We were also interested to see what happens when we have a different number of free parameters, as well as which of these parameters could be effectively predicted using our models, and whether there are parameters that are more problematic than others. Lastly, we tried to look at the kinematic region from which our data is sampled by, and whether shrinking or expanding that region could have a different effect on our model and training. So to answer those questions, we employed on two searches, one on the kinematic space, and we had a whole kinematic space region that the data was concerned with. So the entire global data sets, and we worked from 10% of that data set up to the entire experimental kinematic space. In addition, we also did a parameter search, working from 2 to 25 free theoretical parameters in our models. So some of the initial exploration on 10% of this hyperbox is shown below. So we see that we move from a number of parameters of 2 to 10 free parameters, and we have used to compare 3 of our models. So the chi-squared loss that we have defined before is what is most important in this comparison. And we see that the JAM code, so the code base, the regression fits, actually come up with a chi-squared of 1. And as a result, our machine learning networks will be effective also if they have a comparable chi-squared result of around 1. So in the space of 2 parameters, we see that all our models are doing pretty well and are comparable to JAM. However, when we move to the 10 number of parameters, we see that our mixture density network is actually becoming less accurate, and our chi-squared is becoming increasingly worse. However, what is hopeful for our results is that by using this MDN in an embedded architecture of autoencoder, we actually can get the result back with the accuracy that we desire. And so the fact that we get the chi-squared back to 1.04 is very hopeful for our architecture, and we see that the AEMDN is performing better than both of our previous models. In addition, we look specifically at the different parameters that we are predicting. And so we have here plotted all of the 25 free parameters individually, and we have predicted their correlation, their Pearson correlation with the JAM theoretically predicted parameters. And so a Pearson correlation of 1 means most correlated. So we have in blue, orange, and gray, the AE, AEMDN, and MDN predicted parameters. We see that MDN and AEMDN, because of the embedded MDN architecture, are not as effective in predicting some of these parameters. And we believe that this is possibly stemming from the fact that some of these parameters do not have a set distribution. And so it is harder to try to use a mixture of Gaussians to predict them. Lastly, We also have a blind test result that given one JAM solution, so basically given one theoretical cross-section that we know the parameterized solution of, we use our autoencoder architecture model to try and see whether our solution will be close enough to that of JAM. And so the percent coverage here has gone up increasingly. So we have tried 2 different blind tests, one with 75% coverage, so a really big part of the hyperbox of the global data set, and then a 50% coverage, but with an increased number of 25 parameters. And we have used the autoencoder for this specific test because of how big the space of coverage is. We want to see, can we get the most accurate solution that JAM gives out? Very good. And as a result, we see that both of our predictions are actually very close to the chi-squared of 1 that we really want to get near. And so we're confident that this autoencoder model can actually be almost as good as the JAM architecture and code base. On the left, we plotted this last blind test in PDF space. And so these are 4 of the important PDFs we want to look at. And we see that in the PDF space as well, we're very closely correlating to the true, which correlates to the JAM PDF predictions. And so we're within 1 standard deviation of the PDF graphs that JAM is also coming up with. So lastly, this semester, I'm working on my honor thesis, and I'm actually continuing some of this work. My work is a little different because I'm using a GAN, which stands for a Generative Adversarial Network. And I'm using a GAN for data generation. So basically a GAN is a model that generates data that follows a distribution. And what I'm trying to do is generate parameter and cross-section pairs. And these pairs will be really useful for researchers using global analysis. So the way my GAN works is that we have noise coming into an MMD and WGP GAN. So the generative adversarial part actually creates the parameters, which are then mapped using a forward mapper into cross sections, and then their discriminator actually makes sure that they follow the distribution of their real cross section data. And as a result, because we have only a certain amount of data points right now used in our different research methods and global analysis, this is going to help researchers in their tools in global analysis and hopefully help accelerate research in the field. Some of the preliminary results are shown on this table on the right, and they're showing how closely our generated points and generated outputs of parameters and cross sections actually correspond to the real experimental data from different experiments. And again, the desirable chi-squared that we need for this is 1. And so we are achieving this for some of the experiments, but still have some progress towards some of the most harder experiments to fit, such as NMC and SLAC. Thank you.
All right, thank you, Eleni. Let's everyone again give a resounding virtual silent applause. And Eleni, you have all these people applauding you from their homes, I promise. Yeah, thank you so much for that. We have like 9 minutes left for questions. I also wanted to point out, now that we've all listened intently, that Eleni and Braden are both senior undergraduate students that are applying to graduate school right now. So I think that this is really incredible work. They full ownership of these projects to have done at this level. And so we are opening up the floor for questions. And I think, so I see that people are not finding the raise your hand feature. And since I last used Zoom, it did move to the reactions button. So you can either write in the chat if you can't find it that you have a question, or you can raise your hand. So what questions do we have for Eleni? Pablo.
So just a comment, at least for me, you click on participants and in there you have the raise hand. But I have a question. I didn't just do it to say that. So one thing that I wanted to understand better is what is the advantage of you having multiple solutions. When you were saying that you use the Gaussians as an output to have kind of a distribution that doesn't look like a bomb, but a collection of bombs, why is that important for those type of experiments?
Right. So basically, there's two ways in which multiple solutions are important. One is simply the uncertainty of the experiments. So basically, the uncertainty leads to different parameterizations that can be accurate. And as a result, because different parameterizations can be accurate, we also want those parameterizations to be able to come out of machine learning models, since they're able to come out of different fitting models using regression. The second one is just physically. We have observed that different collaborations have physically found, not because of uncertainties, but because of the nature of the problem, parameterizations that are actually accurate predictions of those cross sections and parameters. So there's both the uncertainty part, but also the actual multiple solution part physically that exists.
Yeah, so the cross-section data experimentally is known at very discrete points with uncertainties. And so if you're doing the inverse problem, you may expect maybe you would just get a distribution around one parameter set with uncertainty, but that's not necessarily true. It can also map to maybe distinct areas of the parameter space as well. Okay, is that sufficient, Pablo?
Yeah, I just want to, if there are no more questions, I want to comment on that. But
we have 2 more questions.
Then go for it. Go for it. I will annoy it at her later. Thank you.
Okay, Harrison.
Yeah, thank you for this very nice talk. And actually, I'd like to make a comment actually about the question that Pablo asked. And I think, if I understand correctly, what you're trying to do is that you're trying to build a probability distribution over the space of the parameters that are inferred, right, from the data. And that makes sense, because after all, this is an inverse problem, which means therefore that there's information that's lost. And so that fact should be reflected in there being uncertainties attached to the parameters that you infer from the model. So I think rather than saying that you're looking for multiple solutions, I think it's probably better to describe this as saying that you're trying to basically apply, place uncertainties on the parameters that are inferred, which I think is actually very important, because as you can see from the plots that you showed, I'm sorry, that even, I mean, there are discrepancies between different groups who do these PDF fits, and it is important that any method that one arrives at should somehow reflect that fact.
Right. Yeah.
So I do have one question though, which is, and it's just a clarification. In the model that produces these multiple parameters for the Gaussians, the mu, sigma, I'm just make sure I understand this. So do you have multiple sets of triplets in the output? Let's say I wanted to have something with, say, 4 Gaussians at the end. Do I have essentially 4 sets of 3 output parameters? Is that how it works? I'm just trying to understand.
So one of them is just the mixing coefficient. So there's only one pi.
Okay.
But then you have different U's, so 3 different U's and 3 different standard deviation. Yes.
So,
okay.
Eleni, I think, yeah, just to clarify, so you're talking about the mean, standard deviation, and mixing coefficients of the Gaussian outputs is what's coming from the model.
But if you want to have, say, 3 Gaussians at the end, then presumably you have 9 outputs. Is that how the thing works? Okay, thank you.
Yeah.
Very nice talk.
Charles.
Hello. Just like to say, great talk. I'm also senior undergrad working on my honors thesis. So I was actually going to ask a question. Hopefully I can apply it to my thesis, at least my research. So, and apologies if this question has already been addressed, because I was in a research meeting before and I joined a little bit late. Basically, what I was going to ask is, when you're trying to come up with solutions for the possible parameters, is it simply just like an an estimation of the error on the parameters, or is there also like a distribution of like a probability distribution of what each parameter is going to be? So for example, like for my research, it's astrophysics, right? And so there's a variety of, there's a range of possible solutions for these parameters, right? And so I want to know, could I use this method to estimate like, how do I say this? Like the range, not just the range, but also like the fraction of each parameter value out of like total parameter space. Does that make sense? I'm sorry if that's not totally clear.
I think that makes sense. So basically what you're gonna get out is 25 dimensional Gaussians, and then the sampling of the Gaussians can actually give you different parameters, and for each parameter you will get a different sampling, right? Because it's 25 dimensional. So for each parameter you could actually get different sampling. It's not like a one set thing. So I think that could work for your research as well.
Okay. All right. Thank you.
Anselm, this will be our last question because we're running up on time here.
Yeah, sorry, I'm not sure how relevant it is again. So it was again choice, if I understand correctly. So basically, you have these multimodal Gaussians for each of these parameters, and you sample from that. So basically, you basically have several outputs of these. Now, so for each parameter in the fit. So if like maybe one remark. I mean, the one question is like, how do you decide how many Gaussians you put in that? Is that somehow driven by the theorem model? And the other remark was to kind of motivate by saying, okay, different theories come up with different solutions. But I see that within the jam, they kind of have this different, kind of minima. So that kind of, motivates certainly, multimodal Gaussian. But the main difference between different groups is that they use very different parameterization. Also, I'm not sure if then this model of saying, okay, each of these Gaussian, corresponds to different fit from different group is really applicable, because the parameters mean very different things. They might have a different number of parameters.
Right. So the first question is actually really important, and like the thing about this is that you can set a maximum, right? Like you can set 5 Gaussians or 10 Gaussians, and the model is actually going to fit itself to as many as there actually are, because some of them will collapse and some of them will be close enough where you can actually realize that because they're close enough, they actually correspond to one larger peak. So that's a problem, but it can, sorry.
So it's basically driven by how much computational power you have. So ideally you have like 100 Gaussian, but then they kind of like resolve.
Right. And then when you realize that some of them have collapsed, you can actually run the model with less Gaussians and kind of do a search of what's needed. The second question, that's actually a really good point as well. I think it depends on training with different data sets, and we haven't really tried that yet. So we haven't tried different collaboration data sets. But it would be interesting to kind of mix the two and see how the model would react to that, and whether we could like realize that there's 2 different ways of fitting the data.
Well, the data is presumably the same. It's just that your networks are probably different because the whole parameterization is very different.
The inputs are the same, but the outputs may be different. Yeah. And I think your second question is definitely a much like bigger question, bigger research question that like, yeah, we are interested in, but it's not like we have not gotten.
No, I understand. It was just a remark. I mean, that's a really good point.
Yeah, and since it's supervised, we would need like the output data as well, and then we could see how it would know for the same input. If we give it 2 completely different output values, how would it react?
And you don't have a bad conscience that you make all these poor theorists unemployed.
We need the theorists. Yeah, thank you so much. I think one last note that I'll make just with respect to the 2 projects is yeah, you can think of Eleni's predictions as these probability distributions, but we kind of wanted to make it clear that, you know, Braden did a full Bayesian analysis, so he could make stronger kind of confidence interval type statements about the output versus Eleni. So, but yeah, they both are quite related in that sense. So I just want to, again, thank both of our speakers and thanking all of you guys for attending. I thought that there was some really rich conversation here, and I'm glad that we could all gather and have this conversation. So with that, I think we can all give everyone a round of applause again and say goodbye.
Bye. Thank you so much.
Yeah, this was great. Thank you. Great. Bye-bye.